So welcome to this first Yagswa, yet another Getting Started with Arduino video. These videos, this series of tutorials is really going to be focused on the things that are near and dear to my heart on this channel, and hopefully near and dear to your hearts as well, which is really things like miniature building, terrain, role-playing games, things like model railroading. I get a lot of questions from model railroaders on how to use some of these things. And again, hobbyists like scale modelers, where you want to add a little bit more oomph or life to your projects. Microcontrollers are a great, Arduino in particular, in my mind, are a great way to add a little bit of pizzazz to your project, bring life and motion and interactivity to them. So for these tutorials, I've got this super starter kit from Elegoo, this Uno R3 project kit. This is not a paid endorsement. This is not a sponsorship. Elegoo is not shuffling buckets of money for me to use this for these tutorials. But I've picked this for really two reasons. Reason number one is I use the Arduino Nano, their clone, a lot in my projects. It's at the right cost point. It's the right quality. I haven't had a dead board yet that I haven't actually killed myself. And so I really do like Elegoo as a brand. I feel like they strike a good balance between quality control and price point. In this case, this kit has all sorts of things that we will need down the line. And so we don't have to go and cobble together a bunch of stuff to continue to dive deeper and deeper into what we can potentially do with an Arduino microcontroller. So I think this is overall a great starter set. I'm going to grab immediately from it. The first thing is the board. Affiliate links down in the description if you want to pick up one of these bad boys for yourself. Obviously, that helps the channel. It allows me to continue to make content, and it is very much appreciated. I will try to keep as much as we can humanly possible, keep limited to the starter kit. If we need something that isn't included in the starter kit, I'll let you know. We'll try to keep that to a minimum. A couple things that I think we'll probably need out of the box is some form of RGB LEDs. These are something I use on almost every project, so we'll need to pick up some flavor of these when we get to that part of the tutorials. And then the first thing that you might consider is picking up a little bit more consistent power supply. This comes with a battery. It also comes with a breadboard and a breadboard power supply. But what it's really lacking is a long-term consistent power source. And so picking up something like this 9-volt 2-amp power supply, this wall transformer, very inexpensive, will help us power our projects without the need of swapping out expensive 9-volt batteries or keeping it constantly tethered to our computer. The computer is a great way to initially power your board and do some programming, but long-term, it may not provide enough juice for the projects that we'll be working on. These we can plug right into the breadboard power supply, power it very consistently, and not worry about accidentally not unplugging it so that the battery drains while we sleep at night. So this is a good one. Again, affiliate links in the description if you want to pick one of those up. So I'm going to set this aside. We're going to get back into that more later on when we start to dive a little bit deeper, dig a little bit deeper. But what I want to talk about in this video really is helping you, for those of you who really are really new to this, understand A, what a microcontroller is, what a microcontroller is not. And then we're going to zoom in on these and we're going to do a quick run through of what some of the big components are, where it's relevant to us, and then understand what all of these little pins, and we'll explain what pins are. It was a kind of a confusing concept to me when I first got started, what they are and what they do. So first of all, These all kind of look the same. They're about the same size. They've got stuff stuck on the board. They've got these input output pins. They've got these rows of things that it looks like I can plug stuff into. But these could not be more different, really, when it comes right down to it. These are microcontrollers, Arduino-based microcontrollers, and these are Raspberry Pis, but more importantly, these are what we would consider or call a single board computer. So this is a full-blown computer with an operating system. In the case of Raspberry Pis, they're based on Linux. They have everything that you would expect from a computer, with some variation depending on the size of the board. This is a Raspberry Pi 4. This is a Raspberry Pi Zero. So they're a little bit different, obviously, because we've got different amounts of space. But you have things like USB connection. This is a network connection. Here we have HDMI inputs, our USB-C power. These are general purpose input outputs, which make them feel very microcontroller-y, and that's what they are actually there for, is to connect to and communicate and build out from this computer. But these are really run off an operating system. You can boot them up in a Windows-like environment. It's Linux, but it's it's got Windows with menus and a mouse and a keyboard. And so these are very much a computer. And it's cool that you can have a computer that basically is the size of a pack of gum, that fits in the palm of your hands, and you hook a couple peripherals up to it and you're rocking and rolling with a computer for all intents and purposes. Very, very cool stuff. They do require a more in-depth understanding of programming for these environments, and they're really way overkill and way beyond the scope of what we would need for our microcontroller-based projects. These are really helpful and useful when you need the horsepower that comes along with it. And by horsepower, I mean things like the ability to do many things at once, or the ability to process video, for example, because these do have video processing on board. So there are times when you might exceed what a microcontroller is intended for and need to move up to something a little bit more robust. We're going to set these aside for now. They're very cool. I love Raspberry Pis. I've fiddled with them a lot. I've made a lot of little computers in a box that are fun and cool and self-contained. But for most of the projects I work on, what I really need is a microcontroller. And so really it says it all in the name. Micro meaning small, controller meaning it controls things. And so in a nutshell, at the highest level, what a microcontroller is going to do, and Arduinos are a family of microcontrollers, is they're going to have the ability to sense things in the outside world, think about what's going on with those sensor readings with that information it's receiving, and then do something, control something in the outside world microcontroller. So in, manufacturing automation, microcontrollers, that's where they all kind of started from. You need to measure the temperature of something, and you need to either turn the heat up or turn the heat down. So you need a microcontroller for that. Well, Arduinos are really a great environment, a great platform for the hobbyist, because they are extremely easy to use and very, very approachable. If you have absolutely no experience in programming or microcontrollers, by the end of this series of tutorials, you will be able to do all sorts of fun, cool, and interesting things with an Arduino. I won't guarantee it, because then I probably am entering in some binding legal agreement, but I will say I have a high level of confidence that you will be able to do that. So let's talk a little bit about what we're seeing here, that is the difference between the three boards. Now, these are all clones, and I may have mentioned this earlier. This is an open source project, the Arduino project. These are clones. These are made by Elegoo. There are many clones out there, and you can also buy the actual Arduino boards from the Arduino organization if you'd like to continue to support their development and fund them to continue to grow the Arduino ecosystem. Not necessary, but it's really, it is up to you. A lot of times people feel very passionate about funding the originator of things. What we have is a Nano. So this is an Arduino Nano. This is basically the Arduino Uno, even though these say Elegoo, these are Arduino form factor, and then Arduino Mega R3s. So these are release 3s, or the version of the board. You will see a lot of different Uno versions. They all have sort of a legacy. And out on the market, there might be old boards, newer boards. It's a constantly evolving world. The main difference, obviously, apart from the size and the amount of components on the board, is really the main difference is the amount of inputs and outputs on the board. That also means that each board will have slightly different processor capability, speed of processors, the amount of things the processor can handle. There might be differences, there will be differences in the amount of code that you can load and store on it. There might be some differences in how fast the processors run. So each board has a bunch of specifications that you can go and look up and dig into your heart's content. But really at the highest level, most of that stuff we really don't at this point need to understand or know. What we really do need to know is that on the Mega, for example, there are just a truckload more of inputs and outputs. So if you're working on a project that has a lot of things that are plugging into it that are pin hungry, that need a lot of inputs and outputs, you may run out if you're using an Uno or Nano. These two are actually quite similar, very similar. The Mega is really sort of the beefed up version of the group. So we're going to actually move the Mega aside here, and we're going to look at the Uno, and we're going to look at the Uno sort of in depth, but I'm going to keep the Nano kind of by its side. And the reason being is the Uno is a great board. Like I said, it's kind of the OG, but the problem with the Uno that I have is it's just really big. And so it's big, it actually costs more for obvious reasons. There's just more stuff on it, and stuff costs money. So there's more things on it, it costs more, it's big, it's not more capable than the Nano. And so I prefer being able to have a much smaller form factor that doesn't have like these big barrel connectors, this gigantic USB connection that most people don't even have cables for anymore. And so I really do like the compactness of this. When you think about it, the Nano will fit very nicely in the fuselage of a model airplane, the chassis of a vehicle or a tank. It would fit in a railroad car quite nicely. When it comes to squeezing them into a chunk of, terrain for a rope RPG game, you could get this squirreled away and maybe run it off of a little coin cell or a battery or two. Some sort of powering this would be sort of the interesting one as you get smaller, but these are really nice and compact, and obviously fitting it into a bigger chunk of terrain or a book nook, it's a no-brainer. These can fit in all sorts of crazy spots. Not too crazy. Let's, keep it clean on the channel here. So we basically have a very compact form factor. It's also, again, because there are fewer things on the board, you can get more Nanos for the price of an Uno. So that is always a good thing, because occasionally I've been known to burn up a component on a Nano board. It happens, things get wired wonky, and things turn into little blue puffs of smoke. You should avoid it, but you should also kind of prepare yourself that is a real possibility in the world of making. We've all kind of done it. So what I'm going to do is we're going to zoom in and we're going to do a little bit deeper dive into the Uno, but we're going to keep the Nano side by side for comparison. So let me zoom in and we'll be right back. Now that we're zoomed in, we're going to just take a look at the biggest components first to just get our heads wrapped around the landscape of the board. The first thing we're really going to interact with that's kind of really fundamental and the most important is the USB connection. This is how we're going to connect it to our computer. And this is initially how we will power the board. The USB connection from the computer provides 5 volts of power in. These are 5-volt boards, and it will allow us to load our programs onto the board. It will allow us to listen to information coming back from the board so we can actually make sure that the things that we think it's doing, it is indeed doing, and power it all at the same time. So we have this big kind of older style USB connection here, a smaller USB mini. It's not quite micro yet or C, but this is a USB mini connection. And that is how we will connect to the computer, and we will connect our initial sort of powering of the board. Next to the USB on the Uno, we have a reset button. That's also found over here. The reset button, think of that as the IT did you restart it reboot button. It will basically reset the microcontroller to its initialized state. It'll bring it all the way sort of back to the beginning of its running routine and let it start over. It's really kind of, I don't know. It's interesting. A lot of times you will want to reset it. But for the most part, if you're having issues with your code and things are weird, rebooting is probably not going to fix it. It's probably something you got to go in and tweak a little bit in either your connections or your setup or the way that you're kind of thinking through your application. So while it seems like it's a cool thing to have that I can just quickly push it and reset it, for the most part, I don't use it that much. A power cycle will do the same thing. Turning it on and off is kind of a similar sort of deal. We have, from a power perspective on the Uno, we have this barrel jack, which will take from 7 to 12 volts. So we talk about how this is 5 volts in that's powering the board, and the boards are 5 volts. When we're powering it from an external source like this barrel jack, or when we start talking about the pins from the pins, it needs 7 to 12 volts. The board needs 7 to 12 volts. And the reason is that when you are powering it, there is a voltage regulator. There's actually 2 on the Uno. There's a 1 here and 1 here. This is a 5-volt voltage regulator, and this is a 3.3 volt voltage regulator. It needs some headroom. It needs some voltage above and beyond what the voltage is that it's trying to regulate to for it to work efficiently and be happy. So 7 to 12 volts are the specs for the board. And I will generally run in about 9 volts into the project. 9 volts is one of those voltages that kick around. There are 9-volt batteries. You can easily find 9-volt power transformers. It's just sort of one of those voltages that are standard. 6 is another one that you always hear. Oh, it's a 6-volt or a 12-volt or 9-volt. You generally don't hear someone saying, oh yeah, I got that 7-volt thing. So those are just the right number of voltages. And honestly, those are all based on the battery voltages. Most batteries like AA, AAA, D cell, C cell, they are all 1.5 volt cells. So everything is a multiple of 1.5. So that's why we land there. So 9 volts is what I'm going to generally be using into the barrel plug. You'll notice there is no barrel plug on this. It wouldn't be very nano if you had a big old chunky piece of plastic slapped onto that. And I actually am not a huge fan of these barrel connectors when it comes to a fully blown, fully realized project in its environment. They're big, they're bulky. You actually have to have a plug that plugs in. That plug is big and bulky. It's kind of hard to squirrel that away in compact wiring. And so I don't love the barrel connector obviously on this board, or not obviously, because we're actually just diving for the first time here. There are some other ways to get power into the board, but another reason I love the Nano is it can be very, very compact in its wiring because it's missing some of these bigger, chunkier components. Of course, obviously that also keeps the price under control. So we talked about reset button, USB power, and our voltage regulators. On the Nano, the voltage regulator for 5 volts is on the backside, There is no 3.3 volt regulator, even though we still do have 3.3 volts available to us, but that is actually managed through some wizardry, some voodoo with another circuit on the Nano. They do a little bit of wizardry and magic to step down some voltage to get us to 3.3 volts. Other things that are on the board, these are our crystals. So this is the clock. We've got a little clock over here, tiny little one. This is how it helps drive how fast the processor runs. These are our processors. So obviously these are the brains of the operation here. The other thing that we'll have that are going to be useful are some LEDs. So these little ones are LEDs. There are 4 of them. So we have this on the Uno RX for receive, TX for transmit. The L LED is actually connected to one of the pins through a resistor. This is actually what it allows us to do is actually toggle that pin on and off, and that will blink the LED. It's actually kind of a nice way for us to make sure that everything is working and that we actually are getting we know what we're doing and we are getting the results that we expect. There are no issues with the processor. There's maybe not any, there's no issues with the way that it's set up and it's all ready to go and everything is right in the world. So that is what that L LED can be used for. And then there is an on or a power LED. So this, when we power up the board, this will light up. If it does not, you want to go back and check to make sure you've got power coming to the board, your battery's not dead, or you haven't reversed your voltage or ground, or you've got some other weird power issues. Or worst case scenario, there's an issue with the board. Over on the Nano, we have receive, transmit, power, and that little L LED. Okay. I think that's kind of the big things that we really need to know about. It's important to understand that not that this is the voltage regulator, but it is important as we work on projects to understand what the power requirements are for the board, what the power capabilities are for the board, what power can it deliver. And that way we are going to make sure that we don't actually damage the board by trying to do too much with it or push too much power into it. So those are all important things to note. And then obviously, where do we connect our USB? And what do these blinking lights mean? So that's kind of the big chunky parts. The next thing we're going to look at are the pins. And so this is something that was confusing to me. I'm kind of easily confused at times, and this was sort of mystical and magical to me. I didn't understand how a pin, and this is an example of, these are examples of header pins that you would see. These are male header pins. These are on that Raspberry Pi. These are female header strips. You plug things into, you connect things to these header pins, or in the case of the Nano, you could actually just solder directly into the solder pad. But I didn't really understand how these pins could do so much. How could they be power and power on and off? And how could they send signals that are communication? How can they measure voltage? How can one thing do so much? And it's really actually not complicated if we understand a few basic concepts. So what we're going to do is we're going to start with what I would like to call sort of the utility pins. There are really 3 main buckets of pins on these microcontrollers. We're going to say pins all sorts of times, so sorry in advance. That's going to be the word of the day. So on the utility side of things, we have these power pins. They're also over here. They're kind of scattered around a little bit on the Nano. But this row of power pins starts with here our voltage in. So this is if we wanted to not use the barrel connector and we wanted to wire in power from an external source, we would use the voltage in for our positive. We've got a couple of grounds. We would just use one of those grounds for our negative. And again, 7 to 12 volts, that is our magic range. So that would come in, voltage in, ground, ground. We have 5 volts here. This is 5 volts out. So this is coming off of this voltage regulator, and it's making 5 volts of regulated power accessible to us to the outside world. And the same for the 3.3 volts. It is allowing us to power 3.3 volts out. The reason 3.3 is on board is because a lot of sensors actually out there in the Arduino microcontroller ecosystem use 3.3 volts as their power. And it's just a nice way to keep your wiring and your systems, your setup a little bit cleaner. You don't need to try to sort out another voltage regulator to step down your voltage to run your sensor. So it's a very nice way for this to create a very interchangeable ecosystem. So this is 3.3 volts out. Here is a reset pin, which is able to allow us to basically, do some things similar to the reset button. And that is kind of the power side of things. There's some reference pins that we won't really talk about unless we need to talk about them. I've honestly, in the simple projects I've worked on, I've never used them. I've never actually even used the reset pin. So if they come up and rear their ugly heads, you know where to find them. There are limits to the amount of amps, the amount of current that all of these pins can deliver, and we'll talk about that in the second video, or maybe down the road when we start talking about how we create circuits for these projects. All right, those are the utility. Again, on the Nano, we've got VIN, ground, reset, 5 volts. 3.3's jumped over here, and we've got a ground kind of snuck in over here. And so they're all kind of scattered around in a little bit different configuration on the Nano, because they just need to be more efficient with the space. Making circuit boards can be quite challenging, especially when they're tiny. That leaves us with really the pins that we are going to think about, use, and deal with the most. And there are 2 types, basically: analog and digital. And the way to think about these is to think about them in terms of maybe like a record player or a cassette tape. Records are coming, I hear cassettes are actually coming back. So cassettes and records are having their heyday, and digital, which is like a CD. And I'm not sure if CDs will ever have a heyday, but think of them like CDs. Now, an analog signal, as we're thinking about this, think about that cassette tape or that record. The cassette tape has a magnetic surface that is magnetized to varying degrees. And so the amount of magneticness that is on that tape varies, and it sort of fluctuates in little peaks and valleys. The same with a record. It has a continuous groove that spirals into the center, and there are peaks and valleys, but there are, it's rolling. It is not just up and down. It's like up with a gradient, like it comes up and then it comes down, it comes up. And if we think about those, they're kind of like little wave patterns. And those wave patterns, because they are a sort of a continuous slope of change, if we convert that into electricity, we can actually create a little wave and a slope of changing voltage that produces sound through a speaker. So analog signals are basically kind of waveforms. They're continuous sort of changes in voltage, and the analog pins allow us to take readings from the outside world. Primarily, is one of their kind of their raison, is to take voltage readings from the outside world from 0 to 5 volts, measure those, run them through a little ADC, analog to digital converter, that lets our microcontroller understand what the value of those voltages are, and then we can make decisions on what to do with that, to maybe trigger something or control something on the other side of our system that we're creating. So a good example of this might be, I have a model railroad passenger car, and it has a light sensor on it. And as the car rolls into a tunnel, that light sensor the voltage on that light sensor will drop. It will not be receiving as much light. The voltage will drop. We'll detect that, convert it with our ADC to a number, a numeric value that says, hey, once that number reaches a certain value, turn the LED lights on in the passenger cars. Now, if they're in a model railroad tunnel, you're probably not going to be able to see them, but it's a cool effect. And it would be something that's very easy to do with a microcontroller. We're looking at an analog signal, an analog voltage. We're making a decision, and then we're doing something with that information in the real world. We're controlling something. Microcontroller. So analog. On the digital side of things, digital pins are either 1, 0, on, off, high, low. They're binary. There is no fluctuation of voltage. It's either on or it's off. And so the way to think about those is like a CD-ROM. So CD-ROMs work by creating light and dark patches on a compact disc, on the disc, and then a laser reads either the dark patch is there or the dark patch is not there. It's either on or off. And that information is packed in there so tightly that it is creating basically a digitized, a binary version of the waveform or whatever data or information you're trying to store on the CD. And so it's taking those on and off, those pulses of ones and zeros, it converts those. It actually kind of works in reverse. It takes that digital signal, and in the case of music or a CD, it walks it back, it decodes it, and then it converts it to an analog signal that drives the vibration of the speakers. So digital is on, off, yes, no, high, low, 1, 0, right? It's digital. So that's really the big difference here. The reason there are more digital pins is generally the things that we do with the digital pins require more pins. So if we hook up, for example, a display of some sort of a little digital display, they can really eat up digital pins quite quickly. So we usually need more digital pins than we need analog. There are a few unique digital pins. So we have a receive and a transmit down here. These are set aside for communications between things like displays. So transmit and receive, we'll talk about those if we get into projects that really require them. We generally, like in projects, I will generally try to avoid these and use pins higher up on the food chain and just kind of leave those, set those aside should I need to use them. There are some other unique pins. You see that there's this PWM. This stands for pulse width modulation, and there's a little tilde. So if you see a tilde next to the number, that means that that pin is capable on this board for pulse width modulation. And the way to think about pulse width modulation, we say that these pins can be on or off. So pulse width really is, if we're flicking those on and off rapidly, what is the space between the pulses of on and off? How wide is it? Are we flicking them on and off really quickly with a very narrow width, or are we flicking them off slowly and that increases the width? Now, we're talking about very, very, very fast cycles. And an example of how this can be used is if you connected an LED to one of the pins that has PWM, you would turn the LED on by turning the pin high, which drives power to the LED. Now, LEDs aren't like light bulbs. They really don't dim really like a light bulb would if you reduce the power to them. You can kind of, you can dim them a little bit by reducing with resistors and other things, but they don't really work that way. So a way that we can actually control the brightness of an LED is with pulse width modulation. So if we turn it on, we drive the pin high, the LED would be on full brightness. We turn it low, we would turn the LED off. If we actually turn it off really quickly so that it's only on 50% of the time, using pulse width modulation, pulsing it very quickly at a certain number of cycles, our eyes will perceive that as only being 50% brightness. The same can be said with motors. You can use pulse width modulation to control the speed of a motor because you're basically just turning it on and off very quickly, and so it's only on for a percentage of the time. And so that's what that's one of the things, that's really what PWM kind of at its high level is used for. And so hopefully that makes some sense. And we will do some stuff with PWM with pulse width very early on when we start to play with some lighting or with some LEDs. Another last thing to note on pins, they do start with 0, so A0 through A5. So we have it, even though it says A5, we actually have 6 pins. This starts with, on the digital side, 0, pin 0, and pin 13. So we actually don't have an unlucky number of pins at 13. We actually have 14. So 14 pins of digital on this board and 6 pins of analog. On the Nano, we actually have A0 right here through A7. So we actually have 8 pins of analog on the Nano. And then we have 0 on the transmit up through 12 on the digital. There's some other pins sort of mixed in. There's a ground that they sneak in here and a reset. So we have 12 and then 13. Digital 13 is over on this side. So there are again 12, I'm sorry, let me do my math. It's plus 1, 14 digital pins on the Nano. So digital, analog. Analog's like a record player or a cassette tape. Digital's like a CD-ROM. We've got our power. This is our kind of our utility section. And then we have a couple other things snuck around that we're not going to really mess with too much with some reference pins for the board. We've got all of the big chunky stuff sort of called out. We are going to focus on using the Uno. The nice thing about the Uno is it is a really nice development and learning board because there's lots of space. There's a lot of information contained on them. On the sides of the board, we have all of the information that is repeated. So these are really great learning boards. But when it comes down to actually putting something in something, I'm, like I said, a big fan of the Nano. So I hope you found this interesting and informative. This is really especially good if you are really, really new to microcontrollers. In the next video, we are going to talk about how we power the board. We're going to use some things out of the kit. We're going to talk about breadboards and how we're going to use breadboards, powering the board. And then in the third video, we'll really actually start to dive in. We'll get connected to the boards, we'll download the software, set up our programming environment, and do a run through at a very high level of the Arduino programming environment and some very basic concepts. And we'll load our first program into our microcontroller and get the LED to blink. And we'll make some changes to it and start to bend it to our will and make it do the things we want it to do. So, if you found this useful, be sure to hit that like, subscribe button. This series, I'm going to try and keep these going. So hit that bell to receive notifications when I update or post a new video in this series. And again, I want this to be focused on really the things we love and care about and the things that bring you to this channel. So things like miniatures, miniature terrain building, dioramas, book nooks, model railroading, and role-playing games where we can actually bring some interest and life to our projects. Thanks for watching. Thanks for hanging in for the duration of the video if you've made it this far, and we will see you again with another random making encounter, another Yagswa, and we'll talk about power.